In the previous video, we had discussed sound pressure in its general form, with its SI unit of Pascal, and we'd listed pressures ranging from the threshold of hearing to the threshold of pain, and a few common ones in between. Now let's try to plot this on a graph, a one-dimensional scale. Just to make it easier to visualize the scale, let's multiply all the numbers by some scalar value to make them all whole numbers. A factor of 10 to the power of 5, or 100,000, should do as well. Once we scale up the values, we get a new arbitrary range from 2 all the way up to 10 million. Let's plot this linearly, meaning that the difference between any two consecutive plot points is the same. Here, the difference between the points is 1 million, and we have 10 points to make up 10 million. The plot looks ridiculous. All resolution is lost at the lower range of values, where our ears are most active. There's a lot of wasted real estate where we don't really plot anything. And if we do want to achieve a reasonable amount of resolution for the lower range of values, we have to resort to decreasing the difference between the consecutive points, thereby increasing the length of the scale to something larger than this window can hold. Much larger. And another problem with a linear representation is that it doesn't paint a true picture about subjective loudness. For instance, the noise of traffic at a distance isn't 100 times louder to perceive than a conversation with a friend, for example. It's definitely a few times louder, but not 100. The reason why the linear scale is so intuitive for us is that everyday math revolves primarily around addition and subtraction. What we need to do is to forcefully think about multiplication and division. Let's reformat the scale. And instead of the graduations being at every addition of 1 million, we can make it so that the graduations are a multiple of 10 apart. More simply, we can represent them as powers of 10. What we just did here is create a logarithmic scale. It's a really useful scale for representing exponential functions and exponential growth, where the range of values are massive. As we can see, the logarithmic scale is pretty useful in representing our full range of values. Let's look at what a logarithm or log of a number really is. It's just another way of querying the power or the exponent function. Using the power function, we can state that 10 raised to the power of 4 is 10,000. Another way you can frame this statement is by stating that the log of 10,000 to the base 10 is 4. That's all it is. The log function is just a rearrangement of the exponent function. We can simplify this further by ignoring the base of 10, because in most engineering disciplines, base 10 logarithms are the most commonly used variant, and it's implied. In pure mathematics, however, log to the base e, which is the Euler constant, is more commonly used, and it's called the natural logarithm. You can differentiate them in a calculator. Log is log to the base 10, and ln is the natural logarithm with its base as e. Another simple way of looking at it is by counting how many digits or zeros a particular number has. Log of 10,000 is 4, since it has 4 zeros. Log of 10 is 1, log of 1 is 0, and log of 25,000 is some number between 4 and 5. Mathematics out of the way, we can focus on how we want to represent the pressure scale. We'll ditch the scaled numbers and go back to the original table of data. A logarithmic scale is honestly all you'd ever need. We solved the problem of lack of resolution with a log scale. But we can go further. What we can do now is, instead of talking about the absolute pressure value of some source, which isn't particularly useful, we can instead talk about how much more the pressure value is of that source when compared to a baseline standard. We need ratios. We also want our scale to start from 0, because it's nice that way. And we need to set the baseline value against which all of the comparisons are made. What value shall we assign to the baseline? Perhaps the threshold of human hearing? Alright, let's stick with that. So in our scale, any pressure value we want to represent will be compared to the threshold of human hearing at 20 micropascal as a ratio, like so. And to constrain the size of the scale, we'll take the log of this ratio. Beautiful. We've constrained all the pressure values on this table on our new scale between 0 to around 7. Turns out something similar already exists. It's called a bell, and it's a relative unit of measurement used to express the ratio of one value of a power or a field quantity to another on a logarithmic scale. You might wonder how it's similar. Bell is in fact a unit first used in the measurement of electrical power in telephone applications, so it's not immediately apparent how it can be applied to the measurement of sound pressure. If you look closer though, it says power or field quantity. Pressure is in fact a field quantity. Pressure exists in a medium and can be measured at any cross-sectional area of the medium and is dependent on the position from the source. Meanwhile, the source can be considered to be releasing energy over time. This energy is what's responsible for creating the change in pressure in the medium in the first place. Consider this analogy. A heater in a room warms up the room. A heater is rated to some electrical power level, whereby it converts electrical energy into heat over time. This causes the temperature in the room to go up. We can view this from the lens of cause and effect. The heater, or the electrical power, is the cause, and the change in temperature in the room is the effect. They are completely different units of measurement. Electrical power is measured in joules per second, or in watts, and temperature is measured in Celsius. But there's a definite relationship between them, although the relationship can be complex. The temperature that you feel depends on how well the room is insulated, where the heater is positioned, and how far you are from the heater. This exact analogy can be applied to, let's say, a loudspeaker. The acoustical power of a loudspeaker can be considered the source, measured in watts, and the pressure difference that it creates is the effect, measured in Pascal. And a complex relationship exists between sound power and sound pressure, which depends on how reflective the room is, where the loudspeaker is positioned, and how far you are from it. We'll go into a lot more detail into sound power, sound intensity, and why these are purely theoretical concepts. And we'll explore this formula in more detail, which outlines the relationship between sound power and sound pressure. But for this video, if the measurements are done in the same setting, these properties can be considered to be some constant value. And we can see that the power is actually directly proportional to the square of the pressure. Let's use this relationship in calculating the bell. One bell is said to be the log of the ratio between two power quantities. If we substitute power with the relationship expressing pressure, we can see that the constant terms get divided and cancelled, and we are left with a square of the pressure. And by the properties of logarithms, this can actually be expressed like this. And as we mentioned before, we can substitute the baseline pressure value to the threshold of human hearing at 20 micropascal. Most of the time, we want a little more granularity and a slightly larger range of values, so we use the decibel scale instead, where decibel is just 1/10 of a bell and can be expressed like this. This is it. This is the standard and accepted way of measuring sound pressure. We can recalculate the values of the entire table, and this is what we get, where the decibel of sound pressure levels range from 0 decibels at the threshold of human hearing to around 130 decibels as the threshold of pain. Here's an interesting bit, which makes decibels a hairy unit to work with and is a source of confusion for a lot of people out there. When you're talking about ratio of the pressure values, you're dividing one unit by the same unit, which cancels the entire unit out. and thus the decibel is a dimensionless unit. Once it's calculated, you'd have no way to know what it's a measure of. It could very well be a measure of the sound power levels or the sound intensity, or even voltage or electrical power, all of which are valid ways of being expressed in decibels. For instance, saying something like a sound is 60 decibels loud makes near to no sense at all, because it doesn't give you any context of what was initially being measured. To make it crystal clear that we're actually talking about pressure and that we've taken the reference pressure value as 20 micropascal, we append SPL, or sound pressure level, after dB. So stating something like a sound is 60 dBSPL makes perfect sense, since there is no ambiguity about what you're talking about. That about completes our discussion on sound pressure level. But before we wrap up, I just want to explore a couple of commonly encountered questions. Can a decibel pressure level be negative? Absolutely. We've set the baseline or the reference value of 20 micropascal, the lowest our ears can hear. But our measuring instruments can be tuned to pick up pressure values far lower than this in an anechoic chamber. If the ratio between the pressure values dips below 1, the log value turns negative. Next, what's the change in decibels when the pressure is doubled? If we double the pressure, what would that mean on the decibel scale? Let's find out. If a pressure value is twice the original, then the calculation just boils down to 20 log 2, which is around 6 decibels. So every time pressure is doubled in pascals, the decibel scale increases correspondingly by 6 decibels. Similarly, if the pressure is halved, the decibel scale reduces by 6 decibels. Alright, here's the last question. Does doubling the sound pressure double the perceived loudness? Well, it's subjective, as I've already pointed out before. Loudness depends on a lot of factors like the frequency content of the sound, but a pressure increase anywhere between 6 to 10 decibels would relate to a perceived doubling of the loudness. In the next video, we'll take a look at acoustical power and intensity of sound, and how different they are from sound pressure and why they're relevant.